Hi, now in this video lecture we will go through Raoult's law of vapor pressure. Right now, what Raoult did, he studied vapor pressure of binary solutions. Right, so there would be two cases that we will go through of binary solution. The first case is when the binary solution consists of two volatile liquids, and the second is when the binary solution consists of a non-volatile solute in a solvent. Solvent is volatile. Right, so the first case, this solution consists of two liquids A and B, and both are volatile liquids. Right, so when the solution of these two liquids will vaporize, right, so the vapors that are above the liquid surface consist of both liquids A and B, because we know that both the liquids are volatile. Right, so in the vapor phase we have vapors of both A and B, and in the liquid phase we have component A, liquid component A, and liquid component B. Right, and the mole fraction or the moles of liquid component A is called as the mole fraction of A, and the moles of liquid component B in this solution is called as the mole fraction of B. So XP represents the mole fraction of component B in solution, and XA represents the mole fraction of component A in this solution, A plus B. So the vapors, now let's talk about vapor phase. This vapor at equilibrium, when the rate of evaporation is equal to rate of condensation, the vapor pressure above this liquid, right, is the vapor pressure of the solution. Right, and the vapors above this liquid surface contains both A and B. Right, so the total vapor pressure above the liquid surface would be vapor pressure due to component A and vapor pressure due to component B. Right, let's write it over here. This total vapor pressure here is due to vapor pressure of A and vapor pressure of component B. To this, the vapor pressure due to A is called as the partial vapor pressure due to component A, and PB is called as the partial vapor pressure of component B. Right, and the partial vapor pressure, that is the number of vapors that are escaping into the liquid from the liquid into the gaseous state, also depends on the amount of the component in solution. Right, more is the amount of liquid A in solution, more is the number of vapors, more is the number of liquid molecules of A that will pass into vapor state. Right, so we say that the vapor pressure, partial vapor pressure due to component A would be directly proportional to the mole fraction of component A. Right, mole fraction is nothing but the number of moles. More is the number of moles of component A, more liquid molecules due to component A, or the more liquid molecules of component A will pass into the gaseous state to build up the vapor phase or the vapor pressure. Right, so this partial vapor pressure due to component A is the expression for it. It depends on the mole fraction of A, right, and the vapor pressure of pure liquid A. Right, so this consists of entirely liquid A, so PA0 represents the partial vapor pressure due to pure component A. Similarly, for component B, the partial vapor pressure due to component B is equal to PB0, which is the vapor pressure due to pure component B, and XB, that is XB is the mole fraction of component B in this liquid solution. Right, so this is defined as, this is the Raoult's law of two liquid solution of two Raoult's law of binary solution consisting of two volatile liquids. First, it states in a solution partial vapor pressure of volatile component at a given temperature is equal to the product of mole fraction of component, right, and the vapor pressure of component in pure state, right. It's directly proportional to the XA, which represents the mole fraction of component, and the vapor pressure of component in pure state, which is PA0 and PB0, right. So we can write it as partial vapor pressure due to component A would be PA0 dot XA. Right. Similarly, partial vapor pressure due to component B would be PB0 due to, that is the partial vapor, that is the vapor pressure due to pure component B, and XB, which is the mole fraction of component B. Now let's just try to understand this, because we said that the partial vapor pressure due to B is directly proportional to the mole fraction of component B, right. Since this liquid solution consists of A and B, right, so XA is the mole fraction of A, that is the number of moles of liquid A, and XB is the mole fraction of component B, right, that is the number of moles of component B, liquid component B. So the vapors that are above this liquid solution consist of component A as well as component B, right. So the number of liquid molecules that are passing into gaseous state, right, depends on the mole fraction of the individual components. Suppose we have more XA, right, suppose XA is greater than XB, we take more number of moles of component A, right. So we have more amount of component A. So if we have more amount of component A, more number of liquid molecules due to component A will pass into vapor phase, right, to build up the vapor pressure. So the vapor pressure is directly proportional to the mole fraction of the vapor pressure would be directly proportional to the mole fraction of the component, right. More is the mole fraction, or more is the, it's just like a quantity. More is liquid A, more would be the vapor pressure due to liquid A, because more is the liquid A, more vapors will pass into the vapor state. This is what it means, right. So you see this diagram, it consists of green and red dots, means the vapor phase consists of both liquids A and B, vapors from both liquids A and B, and here we have both liquids A and B, right. So this is it. Now let's come to the second case, which is a binary solution of a non-volatile component or a non-volatile solute in a volatile solvent, right. I repeat, the second case is a binary solution of non-volatile solute in a volatile solvent, right. So this is the case where red dots represents non-volatile solute and green represents the volatile solvent, right. So the vapor pressure above this binary solution will consist of volatile component A, right, will consist of vapors due to volatile solvent A. I'm sorry, it consists of vapors due to the volatile solvent, right. So let's first understand, if this solution does not contain solute, does not contain non-volatile solute. Suppose we have this container, right, and it consists of only solvent, right. So if it consists of only solvent, the liquid molecules, the solvent molecules at the surface will have only solvent molecules, right. So the solvent molecules, those solvent molecules that have kinetic energy that can overcome the intermolecular force of attraction on these liquid molecules would escape into vapor phase, right? So the vapors would consist of liquid molecules that are on the surface, right, and have enough kinetic energy to overcome the intermolecular force of attraction, right, on these liquid molecules. Now let's consider, to this pure solvent we add solute, right? When we add solute, this would now consist of solute molecules as well. This solution now consists of solute molecules which are non-volatile. So at the surface also some solute molecules will go and replace solvent molecules, because earlier we have only solvent molecules at the surface. So when this solute is added, this solute will replace some of the solvent molecules. Now since we have less number of solvent molecules at the surface, right, so less solvent molecules will pass into vapor state, right? So when less solvent molecules will pass into vapor state, the vapor pressure above this solution will come down, right? So that is, the vapor pressure would be lowered, right? So this is very important. So the addition of solute would replace some of the solvent molecules at the liquid surface, due to which the number of solvent molecules that are passing into vapor state or gaseous state would reduce, which in turn will reduce the vapor pressure above the liquid solution. Vapor pressure above the, now it's a solution, so addition of solute will reduce the vapor pressure above the solution. So we write it as addition of solute will result into lowering of vapor pressure, right? Lowering of vapor pressure. Now the vapor pressure that is built up is due to only solvent molecules, right? Because we know that solute molecules are non-volatile. So more is the solvent molecules, or more is the number of moles of solvent, more is the vapor pressure, right? Or we say more is the mole fraction of solvent, right, more is the vapor pressure, right? So here vapor pressure, if we define Raoult's law for the binary solution of non-volatile solute in volatile solvent, we'll define it like this: vapor pressure of solution containing non-volatile solute, right, is directly proportional to the mole fraction of solvent at a given temperature. This is what I have just explained. I said that the vapors that are getting built up above this liquid surface consist of only solvent molecules, right? So more is the solvent quantity, or more is the mole fraction of solvent in this liquid, more solvent molecules would go into vapor phase to build up the vapor pressure, right? So we say that vapor pressure is directly proportional to the number of moles of liquid or solvent, right, in this solution. And this is what is Raoult's law, right? It says that the vapor pressure that builds up above this liquid is directly proportional to the mole fraction of the solvent in solution, right, at a given temperature, right? So this is clear, and I've just mentioned it over here. When you added solute, right, this red dots represent solute here. When you add solute, the vapor phase, in the vapor phase, there are less vapors due to this added solute. So less vapors due to added solute, due to which vapor pressure is lowered, right? So addition of solute will result into lowering of vapor pressure, right? And this is your Raoult's law. Vapor pressure of solute containing non-volatile solute is directly proportional to the mole fraction of solvent at a given temperature, right? So I hope all this is clear to you, right? So you have and this lowering of vapor pressure we have studied in the previous video. This lowering of vapor pressure would cause elevation of boiling point, right? Since the vapors above this liquid surface has reduced, right, which reduce the vapor pressure, right? Now we have to heat this solution to a higher temperature so that more liquid molecules can pass into vapor state to build up the vapor pressure, right? And when the vapor pressure becomes equal to the atmospheric pressure, the liquid will start boiling. That's the boiling point, right? So in this case, when solute is added, we have to heat it to a higher temperature because number of liquid molecules at the surface have reduced because the liquid molecules are replaced by solute molecules, or the solvent molecules are replaced by solute molecules. So this will result into lowering of vapor pressure and elevation of boiling point, right? So I hope all this is clear to you. Just remember these expressions for the liquids, right? And this is important. You will get this in numericals, that PA, which is the partial vapor pressure, is equals to PA0, which is the pure partial, which is the vapor pressure of pure liquid, and XA, which is the mole fraction of liquid A, right? So let's go through this. Thanks.